What if human evolution isn't just this, slow march dictated by nature anymore? What if we're right at the edge of a future where we choose our next steps, where technology actually merges with our biology, totally redefining what it means to be human? The kind of stuff some people whisper about. Are we playing God? Or maybe just becoming something more. Welcome to Cool, Weird, and Possible. Today we're doing a deep dive into the, let's be honest, fascinating but sometimes unsettling world of human augmentation. Our mission is to explore how technology is changing us, moving way beyond just treating illness to, well, potentially altering our fundamental human capabilities. And when you think about it, human augmentation isn't some totally new thing, right? We've actually been doing it for centuries.
That's absolutely right. I mean, historically, augmentation was mostly external, often pretty basic stuff.
Like weapons or armor.
Exactly. Think about it. A spear extends your reach.
Right.
A shield boosts your defense. Basic tools extending ability. But the real shift, the thing we're seeing now, is the move from those external tools to sophisticated, genuinely integrated technologies.
Yeah.
Technologies that really start to blur the line between what's biological and what's, well, mechanical.
So if we've always used tools to make ourselves better, stronger, whatever, what was the real turning point? The moment or the tech that actually opened the door to putting machines like inside our bodies, making us more than just tool users?
Well, what's truly fascinating here, I think, is how devices we now consider almost commonplace were the first steps. Things like pacemakers, cochlear implants. They were originally seen as purely therapeutic, just fixing a problem.
Right, helping someone hear or keeping their heart beating regularly?
Precisely. They were door function, yes.
Yeah.
But by doing that, they were the pioneers in integrating tech directly with human biology. They started blurring that line. And this shift, it's already started redefining what we consider normal.
How so?
Well, take someone who has lost a limb. A prosthetic restores their ability to walk, maybe grasp things. That's therapy.
Sure, makes sense.
But what happens when prosthetics get so advanced, they actually surpass natural human ability? Better than the original limb.
Okay. Yeah, I see where you're going.
It forces us to ask, where do we, as a society, draw that line between therapy and enhancement? I mean, think about it. We're already at a point where medical advances mean living healthily into your 60s, 70s, 80s. That's technically species atypical compared to history.
Huh. Never thought of it like that.
So it makes you wonder, right, if the goal was purely average, would we deliberately give amputees, say, less capable prosthetics just to keep them average? It's a striking, maybe even unsettling thought experiment.
Definitely unsettling. And it's not just about bigger, better limbs, is it? We're talking about technology operating inside us on a scale we can barely even imagine.
Indeed. And that brings us squarely into the realm of nanotechnology. It's microscopic revolution. We're now developing technologies that work at the cellular, even molecular level, offering just unprecedented precision in medical interventions.
So, tiny robots, basically. Flowing through our blood, spotting diseases before we even know they're there. That sounds incredibly cool, obviously, but it also makes you wonder, what else could they be doing in there? Is anyone, regulating these tiny detectives? Who's watching the watchers, so to speak?
That's a completely valid concern. And yes, the core idea is moving beyond just fixing what's broken. It's about predicting and preventing breakdown at that cellular level, turning our bodies into these sort of self-monitoring, maybe even self-correcting systems.
Okay.
So for instance, specific types of nanoparticles, you might hear about magnetic ones, or gold nanoparticles, often called AUNPs.
Right.
They're used now to enhance diagnostic imaging. MRI scans, CT scans, ultrasound. They improve the resolution, the contrast, letting doctors spot things like tumors much, much earlier. There are even superparamagnetic iron nanoparticles that show promise for detecting very early-stage cancers. And quantum dots. They offer amazing photostability, tunable fluorescence. Doctors can use them for real-time tracking of molecular changes. Plus, nanoscale biosensors. These can detect incredibly low concentrations of biomarkers, disease indicators in blood, saliva, urine.
So super early diagnosis for things like diabetes, cancer, heart disease, paving the way for personalized medicine.
Exactly. That's the potential. But, and this is a big but, while the potential is immense, the challenges are significant too. There's the high cost, for one, development, deployment, it's expensive. Then there's the lack of standardized regulatory frameworks. How do we ensure safety and efficacy globally?
Right. Rules haven't caught up.
Precisely. And there are legitimate concerns about long-term safety. What happens if these nanoparticles accumulate in the body? Could they affect our immune system, respiratory system, cardiovascular system? We need more research. Addressing all this requires ongoing work, establishing international standards, and innovation always seems to run ahead of the rule book.
Okay, so if we can fix things on that tiny nano level, what about going deeper? Actually rewriting the fundamental code of life itself. I mean, going beyond just managing our biology to actually editing our future selves or our kids.
That's exactly where CRISPR-Cas9 gene editing comes into the picture. It's truly revolutionary, a technology that lets scientists make very precise alterations to DNA sequences right inside living organisms.
Okay, CRISPR. I've heard of it, but break it down. What's the key difference in how it's used?
Well, it's critical to distinguish between two main approaches. There's somatic editing. This modifies genes within an individual's body cells, say, liver cells or blood cells. These changes aren't hereditary, they won't be passed on.
Okay, so fixing a problem in one person.
Right. Then there's germline editing. This alters genes in sperm, eggs, or embryos, and these changes can be passed down to future generations.
Uh-huh. And here's where it gets really interesting and maybe, yeah, a little unsettling again. If we can fix genetic diseases, horrible things like Tay-Sachs, Duchenne muscular dystrophy, cystic fibrosis, Huntington's, what stops us? What stops us from trying to optimize or even enhance future generations? This sounds like the direct path to those, designer babies people warn about. Does this mean we risk losing genetic diversity or maybe creating totally new forms of discrimination based on our genes?
You've hit on the absolute core of the debate. This raises incredibly profound ethical questions. Germline editing, its implications are just huge. On one hand, CRISPR offers this amazing potential to eliminate devastating single-gene disorders. For some really serious conditions, germline editing might honestly be the only way to prevent a child from inheriting the disease.
A strong argument for using it then.
A very strong argument, but the counter-arguments are just as powerful. There are major concerns about unintended consequences, making a change here. What does it accidentally affect over there? You just don't know everything yet. Then there's the philosophical debate around the right to an open future for children. Should parents predetermine their child's genetic makeup to that extent? And yes, your point about enhancement is central. There's a case to be made for a moral imperative, perhaps, to use safe, affordable genetic enhancements for significant health benefits, making everyone more resistant to certain diseases, for example. But on the other side, people voice deeply felt concerns about genetic uniformity. Or worse, the fragmentation of the human race. Genetically superior and inferior
A
groups.
sci-fi nightmare scenario.
It's a scenario people take very seriously. So seriously, in fact, that the UNESCO Universal Declaration on the Human Genome explicitly states the human genome must be preserved as common heritage. It underlines the global weight of these decisions.
So we're talking about altering the blueprint, but what about the command center, the brain itself? What if we could directly connect our thoughts, our actual consciousness, to the massive power of machines?
Exactly. That leads us to brain-computer interfaces, or BCIs. These are devices designed to directly interface with the brain. They enable, potentially, bidirectional communication and control, information flowing both ways.
Okay, BCI, what can they actually do? What's the potential here?
Oh, the potential applications are truly vast. On the therapeutic side, restoring function for individuals with paralysis is a major focus, allowing them to control robotic limbs, move wheelchairs, maybe even communicate verbally again, just using thought signals.
That's life-changing.
Absolutely life-changing. But then there's the enhancement side. BCIs could potentially enhance cognition. Imagine entirely new ways of thinking, of problem-solving, by interacting directly, seamlessly, with computers. There's even research now into what they call collaborative BCIs.
BCBCIs.
Collaborative, like linking brains together, sort of. Integrating brain data from multiple users to improve group decision-making, maybe leading to faster, more accurate threat detection in certain scenarios, or solving complex problems collectively.
Whoa. Okay, so forget just moving a cursor with your thoughts. You're talking potentially what? Communicating telepathically. Or synchronizing your brain activity with others to tackle huge problems. That's a whole new level of connectivity. Elon Musk's Neuralink gets a lot of headlines here, right? Aiming to expand brain capacity, treat neurological diseases. What's the latest with them? What are the big hurdles or controversies?
Neuralink's vision is definitely bold, no question. Their stated goals include restoring sensory functions, enhancing cognitive abilities, all by implanting these tiny electrode threads to record and interpret neural signals. They recently announced they successfully implanted their first chip in a human patient, which is undeniably a major milestone in the field.
Right, I saw that.
But they have faced scrutiny. There were government inquiries, for instance, related to the welfare of animals used in their earlier research trials. That caused quite a stir. Despite those challenges, though, the potential for a profound change in how we interact with the world and with each other is clear.
But it can't be easy.
Oh, absolutely not. The hurdles are significant. Invasive BCIs, the kind that require surgery, carry inherent risks. Infection, scarring, tissue rejection by the body.
Yeah, brain surgery isn't trivial.
Not at all. And the brain's incredible complexity is another massive obstacle. We still have so much to learn about how it really works. And then the ethical concerns are critical. Privacy. Who owns your thoughts if they're digitized and stored somewhere?
That's a big one. What about hacking, if your brain is connected?
Exactly. Security, autonomy, even questions about personal identity. If part of your cognition relies on an external device, who are you? Plus the cost. The current estimate for a Neuralink implant is around $10,500. That immediately brings up questions of equitable access.
Yeah, creating a divide between the cognitively enhanced rich and everyone else.
It's a serious concern. Increased social inequality is a major potential downside we need to grapple with.
So from tiny nanoparticles swimming in our blood to direct brain implants, it really does sound like we're moving beyond just using tools. We're literally becoming, what did you call it, inner cyborgs, from the inside out.
The inner cyborg is definitely becoming less science fiction and more reality.
Yeah.
And it's broader than just invasive brain implants. Think about other body-integrated technologies. There's an advanced two-way acoustic communicator, for example.
What's that?
It's worn inside the mouth, so it's basically invisible. Hands-free communication. It was originally developed to help people with single-ear deafness.
Okay, medical device.
Right. But now, it's being adapted for use by military personnel, first responders. A clear example of how a medical device platform can quickly evolve into an augmentation tool.
Huh, interesting.
Or look at modern prosthetics. We're seeing the seamless integration of sensors, accelerometers, gyroscopes, Hall effect sensors. Think microprocessor-controlled feet, for instance. They provide constant real-time data about the user's activity, their movement patterns, the terrain.
Well, our bodies are becoming smart, generating data constantly.
Essentially, yes. Our bodies, or at least parts of them, are becoming nodes in a network, collecting and potentially transmitting data.
It's like we're building the Internet of Things, but the things are us, our own bodies. And that just raises huge questions, doesn't it? If we're so actively upgrading ourselves from the inside out, what's the end game here? How do we make sure these enhancements, which, okay, often start out as amazing ways to help people, don't become sort of necessary upgrades, things you have to get to keep up, leaving anyone who can't afford them behind?
That is such a critical point, and it's a pattern we see often. Many of these technologies start with restoring function, fixing a deficit, but the underlying platforms, the core tech, inherently allow for augmentation, for going beyond the baseline. The real challenge is steering these developments so they lead to broad societal well-being and don't just exacerbate existing inequalities, especially when, as we said, innovation tends to outrun regulation and ethical consensus. And for many proponents, the ultimate goal isn't just better function day to day, it's about tackling our most fundamental biological limit.
You mean actually outsmarting aging itself, going beyond just living longer, healthier lives to maybe living indefinitely. Is that what we're talking about?
Well, indefinitely might be strong, but certainly radically extended lifespans in good health. The quest for longevity, or what some call immortality, is absolutely central to this. Historically, we've had incredible success in reducing early deaths from disease, accidents, etc. More people reach old age than ever before.
Right. Average lifespan has shot up.
It has. But we seem to have hit a kind of glass mortality floor, maybe around 90 years or so. An upper limit seems baked into our biology. That's where geroscience comes in. The field studying the biology of aging, it's actively working to understand why we age and potentially break that upper limit.
True.
By targeting the actual biological processes of aging through diet, specific drugs, maybe genetics, even cell and tissue rejuvenation techniques. The transhumanist goal here is often termed immortality, not necessarily traditional immortality, but a significantly prolonged life, maintaining good health and function far beyond current norms.
So is living to, say, 300 really possible, or is this just an ancient fantasy dressed up in new scientific clothes?
Honestly, whether we can reach 300, that's still an I don't know yet kind of answer. A few years ago, I might have dismissed it outright. But the science of longevity is advancing so incredibly fast. The very definition of aging as an immutable process is being challenged. We're seeing things in labs, like recent research showing a literal wave of death spreading through dying rat brains that can actually be temporarily reversed with intervention. A reanimation wave, they called it.
Whoa. Okay, that's mind-bending. Reversing death, even temporarily.
It completely upends how we think about the boundary between life and death, doesn't it? If aging is a biological process, maybe it's a process we can influence, slow down, perhaps even reverse in some aspects. So while 300 is uncertain, is there an intellectual reason why the current lifespan limit can eventually be broken? Many scientists would now say no, not necessarily. But achieving that kind of radical life extension would require a huge, holistic, interdisciplinary effort. And it immediately raises profound questions about societal fairness. Who gets access? What does it mean for population resources?
Right. Does it mean only the super rich, the upgraded, get to live these super long, healthy lives? Another divide.
That's the fear. Equitable access is paramount if these breakthroughs occur.
And it feels like the military is often at the forefront of pushing these enhancement technologies too, taking optimization to a whole different level.
Indeed. The military adoption of human enhancement technologies, HET, is a really significant lever in this space. You see it across the board. AI systems are already heavily used for data analysis, predicting enemy movements, things like that. Exoskeletons are a big area. You hear about systems like Lockheed Martin's Onyx or Russia's Ratnik 3 combat suit.
Yeah.
They're designed to reduce the physical strain on soldiers, let them carry heavier loads, increase strength and endurance.
Iron Man suits, basically.
Getting closer, yeah.
Yeah.
And even specialized clothing is being developed, materials that actively regulate body temperature in extreme heat or cold. Beyond that, there's serious exploration of using gene editing, like CRISPR, to potentially optimize soldiers' genetic makeup
Optimize how?
for enhanced performance and resilience. Think maybe improved night vision naturally, or greater resistance to fatigue or specific biological agents. And nanotechnology implants could be envisioned for things like accelerated wound healing or even blocking pain signals directly at the source during combat.
Okay, wow. So if we're actually creating optimized soldiers, is that the ultimate expression of human enhancement? Pushing human capability to its absolute peak for a specific purpose? Or is it just a really slippery slope towards a new kind of arms race? But this time, the weapons are literally human bodies. And who gets to decide what better even means in that context, especially when you're talking about enhancing people for conflict?
These are exactly the profound ethical questions these military applications bring up. Justice, equality, privacy, they're all in play. And there are practical considerations, too. What happens if there's an over-reliance on these technologies? Could it actually reduce flexibility, adaptability, human ingenuity on the battlefield if the tech fails or encounters something unexpected?
Good point. Less resilient if the power goes out.
Potentially. And the sheer cost of developing and deploying these advanced enhancements across military forces. It raises huge questions about resource allocation, budgets, and the potential for creating even greater imbalances between nations.
It just feels like we're stumbling around in the dark here sometimes, making these enormous decisions about the future of humanity, really, without a clear map or even agreement on the destination. With so many different players, governments, corporations, researchers, billionaires, and so many competing interests, who's actually driving this? Who's in the driver's seat of our evolution now?
That's precisely the issue. There is no single driver. Innovation, as we've said, often moves much faster than any regulatory process can keep up with. And trying to halt or control technological progress globally is inherently difficult, maybe impossible. Take nanotechnology again. If one major country decided to ban certain research lines,
Others would just keep going, maybe even faster.
almost certainly, making any kind of unified global front incredibly challenging. There's no single unified decision-making entity with the power to just say, stop or go this way for all research worldwide. So this requires a really fundamental shift in thinking. We need to move away from hoping we can somehow perfectly predict the future and control it. Instead, we need to focus on building healthy, resilient institutions, ethical review boards, regulatory agencies, public forums, and fostering robust, informed public deliberation about these complex issues as they emerge.
So more talking, more oversight.
More talking, yes, but also more effective structures. Organizations like the FDA in the U.S. dealing with combination products, or the NIH's Recombinant DNA Advisory Committee, or various European technology assessment bodies like EPTA or the Rathenau Institute. They are working on creating ethical and legal frameworks, but they're often playing catch-up, reacting to advancements rather than proactively guiding them on a global scale. Look, the core of what makes us human, arguably, isn't being passive recipients of nature's dictates. It's our innate desire to understand, to shape our environment, and increasingly to shape our own destinies, our own biology.
But can't help but tinker.
It seems to be in our nature. The real challenge, the crucial task ahead, is ensuring these incredibly powerful new technologies become means to that end, means that benefit humanity as a whole. We need to guide them towards enhancing well-being, justice, and flourishing, rather than letting them lead us down paths with unforeseen consequences or creating deeper societal divides. The collective journey, like it or not, and honestly, we're really just at the very beginning of figuring it all out.
Yeah. It's clear that line between biology and technology. It isn't just blurring anymore. For many people, maybe in many ways, it's already kind of a distant memory. Whether it's through the microscopic precision of nanotechnology or the revolutionary power of gene editing or the direct interface of our brains with machines. We are definitely standing at the dawn of a new era of human evolution, one we are actively shaping whether we intend to or not, for better or for worse. The choices we make now collectively are going to determine the future of human capabilities, consciousness, and really what it even means to be alive. Thank you for joining us for this deep dive into cool, weird, and possible. If you want to keep exploring the edges of what's next, and let's face it, who doesn't, remember to subscribe to our channel for more thought-provoking conversations.